or on this computer. Yeah, so as I said, there's another video corresponding to the class from yesterday where I also solved some problems. They will be obviously different from the ones I'll solve here. So I do recommend that you watch that other video. Basically there, I did some the problems about determinants that I recommended from the announcement, and some others about vector spaces. So today I'll just focus more like on the vector space stuff, because determinant with the problems I did yesterday, they're kind of that was like a good like sample of the problems. Like as I mentioned before, like for the exam, of the 6 problems, I think 2 will be about determinants and the rest will be about vector spaces. So the vector space stuff is a little bit more important. And then I'll upload the video to YouTube, and I'll also upload the PDF notes that I write today, so that you can also have those solutions. That sounds good. But yeah, the exam is still, it's not next week. It's still on April 3rd, just so that there's no confusion. I just thought it made more sense to have like the review session a little bit earlier, so that you could like, have more time to practice if that's okay. But yeah, feel free to interrupt me at any time. I will also be checking the chat. I'll just go slow and do some extra examples, which I think are kind of useful. So the first one, oh, everyone can see the tablet, the iPad. Is that okay? Maybe I should check that. Good. Okay, and the sound, is that fine? It has been a while since I've done this like over Zoom, so just wanted to make sure nothing is going wrong. Oh yeah. I will definitely post the solutions to the assignment. I typically do it over the weekend, so I'll just upload them sometime over the weekend. But you can also email me if you have like any question, like I can help you out. Before you submit it. I also allow in late submissions. So if you are stuck on something, you can email me and I can give you like a hint or something of like that, if that makes sense. But yeah, I'll always post the solutions to the assignments. I'll probably maybe give you one more before the exam, so related to exam problems, so that you have some extra stuff to practice on. Okay, so the first problem that I was thinking about doing, which actually I cannot put on the list, but I think it kind of is useful. So like the numbering refers to the PDF problems. So this is problem PDF 76 on the PDF, which is just to determine whether certain spaces are vector spaces or not. So this is about determine whether S is a vector space or not. Okay, so like here in this problem, I just give you a couple of like different possibilities for what S could be. So let's start with the first one. Some are very similar, so I'll just do like the more interesting ones. So the first set that I give you, it consists of the vectors. Maybe I should have called this like a different number. Use a different name, but okay, it's just like yeah, I'll call this like Y and Z. This makes more sense. It doesn't change anything, but it looks better. Okay, so here we're looking at vectors where the first entry has to be one of the vector, but then the second and third entry can be whatever numbers they want to be. Okay, so we have to determine whether or not that is a vector space. Okay, Well, let me maybe a couple of seconds to think about it. But if someone comes up with a potential answer, like feel free to type it on the chat, or you can also write it, say it out loud if you want to unmute yourself. Excellent. Yeah, actually, this is super important, like to remember, which is a great way to check, I mean, if something is not a vector space. So this is like an important thing. So important. If the vector 0 does not belong to S, well, to a set, then this set can never be a vector space. It also fails the additivity property. It actually fails everything, but the 0 property is actually very useful because it is very easy to kill a lot of possibilities that way. So if the vector 0 does not belong to a set, then this set can never be a vector space. Then this set is not a vector space. Is that making sense? So that is like, if you're unsure, like, on whether something or not would be a vector space, just check first whether or not 0 is there. And if it's not there, you're done. Then there's nothing else to say. Okay. So here, like, it's easy to see that 0 does, right, for this one, in this case, right, 0 cannot be there, right, because since its first entry is not 1, right? So S is not a vector space. Is that making sense? Any questions up to this point? Maybe before I do some of the others on this example, on this problem. In fact, this same argument, this argument also works for example, like the one that was E. So just to put another one from this set, if you have as here now X, Y, Z, W, where X plus Y plus C plus W plus 1 equals 0, right? That again, it wouldn't be a vector space because if you, right, so this is not a vector space since 0, 0, 0, right, does not satisfy the condition for being inside of S, right? Does not belong to S. Because of this one, right, that you see here, let me see if I can point at it. Right, like if you would get 0 plus 1 equals 0, when that doesn't make sense. So you cannot have a vector space because of that. So far, so good. Any questions up to this point? Let's do one that's a little bit more interesting than these two. Where now I give you, this is G in the same problem. I give you X, Y, Z, but now X equals 0 or Z equals 0. Right, so now we're looking at the vectors where at least one, either the first or the third entry is 0, right? So let me give you a minute or so to think of, for you to think about whether this one would qualify as a vector space. What do you think? Is it or is it not a vector space? Any ideas? Well, sorry, the or is used in the sense of at least. So the condition for being inside is that at least the first or the third entry is 0, but that does allow for both to be 0 at the same time. So, right, yeah, I always forget like, it's like if I told you bring pizza or ice cream, in the or is being used in the mathematical sense, like or is being used in the sense that you could bring both pizza and ice cream. It's just that you at least have to bring one of the two, if that makes sense. So it does belong to, like, let me write that. Yeah, okay, perfect. So exactly. So 0, 0, 0 does belong here. So let me just mention that explicitly. So, but that is not enough, right? To know, but this is not enough to know it's a vector space. Because again, like it does belong here because at least one of the two entries, one of the first or third entries was 0, right? In this case, both happen to be 0, but that's allowed in the way in which or is used in mathematics. So the or of mathematics is like both conditions can happen at the same time, but it does fail with this addition property. So for example, let's look at this, like at these two vectors. So if I take v1 to be 1, 0, 0, right? And v2 to be 0, 0, 1, right? Each is in S, right? But what about the sum? The sum, well, it's pretty easy in this case, right? It's 1, 0, 1, and that is not in S, right? Because the condition for being in S is the condition for being in S is that at least the first or the third entry vanishes. Is that making sense? So so it fails the addition property, right? So S fails the addition property, so it's not a vector space. Is that making sense? Is that clear with to everyone what I'm trying to say? Any questions about this one? In fact, if someone is interested, I can even draw what S looks like for you. So just to have like a better intuition of what this set is. So what is like the equation? How does like the equation z equals 0 look like? I don't know if anyone knows this. What does that correspond to on in space? How would you draw this? Right, it just means all the points where z equals 0, so that's like the xy plane, basically. Perfect. And something similar happens with the x equals 0 equation, right? With x equals 0, now you're looking at all the points, right, where x equals 0. That's essentially what people call the YZ plane. So again, if you take multivariable calculus or are taking it at some in the future, this will make sense, a lot more sense. So this is x equals 0. So what, like in this, oh, I'm surrounded by books, so this is useful. So one plane is kind of looking like this, and another plane is kind of looking like this. And so what we're looking at is, you know, like the picture here is like kind of like two planes. The set corresponds to two planes, you know, being glued or stuck together. And so it's not a vector space because you can easily imagine like taking a vector from here and a vector from here, and it kind of the sum will be outside the two pieces of paper, if that makes sense. Which is another way of saying this additivity property. Is that okay? And just to do one more from this list of just know whether it's a vector space or not. Let's do one that is actually a vector space. So just to practice a little bit how you should write that down. So B So this set consists of all the vectors where x minus y equals y plus z. Okay, and I want to claim, I claim that this will be a vector space. Okay, so let's try to check that how you should write it, because it can be confusing. So let's check that this is a vector space. By the way, checking that this is a vector space is not, it is different from just finding a basis. Finding a basis, I would ask for that explicitly, just say like find the basis for this vector space. In fact, we can find a basis here if you want as well, but it is like more work than just like, I mean, it's a different process, like, or like a different thing from just like showing that something is a vector space. Okay, showing that something is a vector space requires showing this additivity property and this scalar multiplication property. So let's check these two things together. So additivity just means suppose that you have two vectors inside of S. If V1, which is X1, Y1, Z1, and V2, which is X2, Y2, C2 belong to S, what I want to do is want to check that V1 plus V2 belongs to S. Okay, so that's what you always have to do when you want to check the additivity property, that if you have two vectors that belong to the set, then their sum belongs to the set as well. Okay. But what is V1 plus V2? That's just X1 plus X2, Y1 plus Y2, and Z1 plus C2. Okay, so what does it mean to check that this is in S? It means that this, like, I don't know if everyone can see that I'm referring to this right equation. It means to check that this is satisfied for this stuff. So this is kind of playing the role of X, this is a role of playing the role of Y, and this is the role of Z. So what I want to check is whether, X minus Y, what is X minus Y in this case? It's X1 plus X2 minus Y. I don't know whether or not this is the same as Y plus Z, but Y is this thing and Z is this thing. Is that making sense? So far, so good. But what do we know? We do know that that holds separately for V1 and V2, right? So we do know that X1 minus Y1 equals Y1 plus C1, right? And we do also know this, we know since V1 belongs to S, right? And we also know that X2 minus Y2 equals Y2 plus Z2, right? Since V2 belongs to S. So, I mean, essentially, if you add those two equations together, you get the one we care about, right? So adding these equations. Is that making sense? So that's why the addition property holds. Is that okay with everyone? So the proof is not, I mean, the proof is actually not too bad. Whenever you want to check that it's a vector, something is a vector space, I still need to do the other part, but each part is not too complicated. It's more like how to write things down. It's more like an exercise in writing to make sure you're writing these things correctly, if that makes sense. The other property was the scalar property. And so this one just says that you have to check that if V belongs to S and C is a scalar, then C times V belongs to S. So meaning that once you multiply a vector by a real number, it still belongs to the set. That's like the last property. But so if you call this vector XYZ, right, then the condition for being inside is that X minus Y is Y minus Y plus Z, right? So again, like you can, what is C times V is CX, CY, ZZ, that which sounds a little bit weird, right? And well, if you multiply this equation by C, you get CX minus CY equals ZY plus ZZ, which is exactly the condition for CV to be in S. Okay, so it's not, again, checking these things are not too bad, but it is useful to see it explicitly. Is that okay? Are there any questions about this? So far, so good. Okay, let's do one that's a little bit actually tricky, which was problem 666. This is like and this is one of these theoretical questions, which is actually pretty, I mean, it does require like some heavy thinking to see what's going on. So let's do it because like I think it's a useful one. I actually wrote it here. So in this problem, A is a M by N matrix. And the rank of A is just the number R. Okay. So this is telling you that there is a vector V. Suppose there is a vector V such that AX equals B has no solutions. So you can find a vector for which you cannot solve the system of equations, right? So this is asking what inequalities can you give between, what inequalities must be true between M and an R. So let me give you a second to copy this because this one is a bit tricky. So it's useful for you to have like a second minute or so to think about it. So this is the part A. Here's A. This is like the first question. What inequalities must be true between M and an R? So let's start slow. What A is M by M. So that means, remember that it has what? It has M rows and N columns, right? Right. So what can you say? Like, so just think about if this were like a 5x3 matrix, right? For example, you have a 5x3 matrix. What could the rank of a 5x3 matrix be? What's the most it could be of a 5x3 matrix? Or like, yeah, just to give some concrete number. So I'm going to type it on the chat. Right. So what you're saying is kind of like the rank cannot be larger than the number of rows, right? Because rank is precisely the number of non-zero rows, right? So the rank, which is R, should be always less or equal to M, right? And this is always true, right? Is that making sense so far, so good? Any questions about this? Everyone good up to this point? But actually, there's also, I can say something similar for the columns, which is less clear, right? But there's like a property I can use. Also, the rank of A should also be less or equal to the number of columns. This is always true, but this is less obvious. There's like a property that I'm secretly using to claim this one. Why do you think it should be? Because the rank of A equals the rank of another matrix, which is very closely related to A. What's that one? Right, the transpose. So the thing is, I see because of this like important result that the transpose has the same rank as A, that kind of changes like what the column, like the columns become rows, and so kind of like the same argument tells you that the rank has to be less than the number of columns. So it's actually a very important thing to know that the rank is always less or equal to the number of rows and less or equal to the number of columns. So this is something that is always true. So yeah, so it cannot this is always true. Okay. But now let's use, use that A equals B has no solutions. So what does it mean? Again, this is a kind of like a theoretical question, right? There was a way to think of the system of equations, if you remember, in terms of like linear combinations. So what does it mean to say that you can solve AX equals B? It means that I can write B as a linear combination of what in terms of the matrix B, in terms of the matrix A. So if I can solve this system, it means B is a linear combination of what in terms of A? In fact, let me make it more concrete, just to have it, just to make it an example that is easier to follow, because maybe this is too abstract. Look at this matrix, which is 3 by 2, right? Imagine I had given you B to be 0, 0, 1, right? So what is A times X in this example? A times X would be 1, 0, 0, 1, 0, 0 times X. And X has to be, since this is 3 by 2, X has to be 2 by 1. So it's XY. Right, so how am I expressing, like, so asking whether AX equals B is the same as asking whether X100 plus Y010 equals B, which in this case is 001, right? So how am like I'm expressing the vector B, right, as a linear combination of what? What is this in terms of the matrix A? It's in terms of the columns, right? So what I'm trying to say is that if the system has no solutions, it means that B is not a linear combination of the columns of A. Is that making sense? So let me write that down again. So this is important. So AX equals B can be solved only when B belongs to the column space of A. So if AX equals B has no solutions, then B does not belong to the column space. Of A. Is that making sense? So so what that means is that so what this is telling you, what this problem is saying, so in this problem we know so B is not, so let's look at the matrix A. A was a n by n matrix. So in terms, what that means is that it has n columns, if you think about it. Column 1, column 2, column up to column n, right? Because it had n columns. And it has okay. So what this is saying is that and each column, right? Each column has m entries. So for example, in our back to our back to the example that I wrote of 1 0 0 0 1 0, that's like column 1, column 2. So here each column has 3 entries. Okay, so the way, so in like if you know, so if B does not belong to the column space, that means that the column space, what's the biggest the column space could be? Well, the column space, like, the columns have like m entries. Like, for example, like the columns here are elements of R3 because like the vectors have 3 entries. So the largest like the space could be is like R3 itself. So what this is saying is that so if B does not belong to the column space, then the column space is not equal or is smaller than Rm. Right, because if it were all of it, then like there would not be anything outside of that space. So what that means is that the dimension of the column space, so the dimension of the column space has to be less than the dimension of Rm, and that, but the dimension of the column space was the rank of A. So rank of A is less than M, so R is less than M. Okay, so that's like the last thing that you can conclude from, I mean, this is like the thing you can conclude from this problem. So like, if you compare it, like what this is saying is that instead of like having like it's less or equal to, sorry, I'll just go into, we always knew this for a fact. This was always true. So if there's at least a vector that is not a solution for, we can say a little bit more. We can say that there's like a strict inequality here. Because it's just saying that the column space is not the entire space. So, okay, definitely this is a little bit trickier, but it's just like a good way to review some concepts. So I thought that's why And the part B of this problem is, why does A transpose Y equals 0 have solutions besides the trivial solution? So that was the second part to this problem. Okay. So what's the space of what was the name? What's the name for the space of solutions? For the space of solutions to the homogeneous equation A transpose of Y equals 0. Right. So when we look at the solutions to a homogeneous equations, that actually formed a vector space. What was the name of that vector space? It was a null space. It is null space of A transpose, right? Because here we are using the A transpose matrix. And there was a formula for the dimension of the null space, right? What was the dimension of the null space of a matrix? It was just the nullity, right? So this gives you the nullity of A transpose. But what was the nullity of A transpose? It is the number of columns of A transpose minus the rank of A transpose. But remember, the number of columns of A transpose is the number of rows of A. And rank of A transpose is the same as rank of A. So this is the same as number of rows of A is M, because A is M by N. And rank of A is R. Okay. But by problem part A, we already knew that this is positive, right? This is strictly positive. This is strictly positive by part A. So that means that the null space is of positive dimension. Or that means that the nullity is positive. Nullity is positive. So if you remember, like these conditions about vectors, homogeneous system, once a nullity is positive, then there are infinitely many solutions. Is that making sense? Is that okay? Any questions about this? Okay, so maybe for the last problem that we could do, let me see if I can do this one in the remaining time. So this last one would be problem 79. It's a bit longer, so it just says find conditions so that yeah, that's actually what I was going to explain. It's not like a notation that I'll use on the exam, but but I had been mentioning it on the PDF if anyone has been reading the PDF. So what that just means is that the vector space, so this just means that the vector space, so that the vector space, which is obtained from linear combinations of these vectors, 4 vectors, it has dimension 3. So the span means like you have a couple of vectors and you look at all the vectors that are linear combinations of them. Okay. But there's a better way to say this, because remember, when you have a bunch of vectors, you can put them into a matrix. So the matrix A, for example, would be A1, A2, -1, -1, 2, 2A plus B, 1, 2, 2, 1, and 2, 6, 6, 3, right? So any vector that's a linear combination of those four is a linear combination of the columns of the matrix. So what I'm asking, what this problem, like that's how would I ask it on the midterm. It would just be like asking for like the column space to have dimension 3. So we want column of A to have dimension 3. Is that making sense? Is that okay? That's how I would ask it. Like just like find conditions on A and B so that the column space of that matrix has dimension 3. I won't use the word span on the exam because I haven't used it on the class. So is that making sense? And so, but what was the column space of A? That's the row space of A transpose, right? So column space of A equals row of A transpose. So we can look at the row at the transpose matrix, right? Hopefully I won't make any silly thing. Let me write it down. Okay. So what's the transpose is 1A to -1 minus 1 to A plus B 1 2 2 1 and then 2 6 6 3. Okay. And so what am I going to try to see? I'm going to try to see when this matrix has rank 3. When is rank equal to 3? Because the moment the rank is 3, like I know that the dimension of that vector space will be 3. Is that making sense? So hopefully it's not going to be too bad. I haven't tried to reduce this matrix before now. So how do you reduce this matrix? You would do like row 1 plus row 2 into row 2, right? Minus row 1 plus row 3 into row 3, and then minus 2 row 1 plus row 4 into row 4. And what's the matrix that we get? Nothing happened to the first one, the first row. Then you get, this would become 0, 0, 0. Then with row 2, you're just adding them. So 2 plus A, then 4. If there's any mistakes, please let me know. Otherwise, this will ruin everything. A plus B minus 1. And then minus row 1 plus row 3. So 2 minus A. And then this cancels. Then this becomes -1 plus this becomes 2, hopefully. And then minus 2 row 1 plus row 4. So 6 minus 2A, I think. Right, and then this is 6 minus 4, which is 2. Okay. And then what? 2 minus 2 row 1 is, this is 5, I think. Is that making sense? Any issues, any typos that you could see let me put show you the two matrices, because again, this is important that is correct. I mean, there's not too depends on how you want to deal with it now, but let's see. So what if yeah, okay. I want to see when the rank is right. Oh, the second row, second column is 2 minus A. Ooh. Second row. Here you're saying this should be 2 minus A. Oh no, okay, good. Thank you. Good. Whew. So yeah, let's say for example, what if you know, so in order to continue, I mean, there are different ways to do this. But what's better? Okay, yeah, I want to divide. I don't want to divide too much. Okay, so I'll just do an exchange of rows first. I will do row 2 with row 3. You'll see why in a second. Okay. So I changed those 2 rows. The only thing is because eventually I still want to divide by 2 minus A. And so since there's an extra 0 here, the division just simplifies a little bit more on this side. Okay. So right, there's a case where okay, there's a case where A equals 2, right? That's what would prevent me from dividing by 2 minus A here. So what happens when case A equals 2? You get 1, 2, 2, negative 1, 0, 0, 0, 2, right? And then 0, 4, 4, 2, this becomes b plus 1. And then what? 0, 2, 2, 5, right? Is that making sense? So far, so good. So I can use the 2 here, right? Turn it into a 1. And with that 1, right, I can make zeros here, zeros here, and zeros here, right? So let me, I mean, there are a couple of steps here, but hopefully they're kind of clear, just so that you see what's going to happen. 0, 0, 0, 1, 0, 4, 4, 0, 0, 2, 2, 0. Is that making sense? Because again, with these 2, I make it a 1, and once I have a 1 here, I can just use it to cancel the negative 1, the b plus 1, and the 5. Is that okay? And then these 2 rows are essentially the same, you can cancel one of the other. And so again, you can do minus 2 row 4 plus row 3 or something like that. So you get 1, 2, 2, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and then you would cancel 1, 1, 0. Is that making sense? So the rank of this matrix is what? It's 3 because there's one non-zero row, a second non-zero row, and a third non-zero row. So when A equals 2, so A equals 2 and B whatever, gives dimension 3. Is that okay? Is that making sense? So now we're back to the general case. Fortunately, on the iPad, you can just copy paste. So let me copy paste this one. Can I? Yeah, I think so. Copy and paste here. So I want to do now 1 over 2 minus A row 2. And this is 1A 2 negative 1, 0, 1, 0, 2 over 2 minus A, and 0, 2 plus A for A plus B minus 1, and then 0, 6 minus 2A, 2, and then 5. Is that making sense? And then I'll do like what, minus 2 plus A row 2 plus row 3. Let me put in a color. We're almost done, I promise. Row 2 plus row 3. And then what? 2A minus, minus 6 minus 2A row 2 plus row 4. It doesn't matter what happens with row 1 because that one will have a non-zero row. So like for the rank, you don't have to worry. If you only care about the rank, like the first row is already good. Like it doesn't need further simplifications. Okay, this is good for 2. Okay, we're almost there. It's just like a bit tricky so to write down. So you would get A plus B minus 1 minus 2 plus A. Oh, yeah, minus 2 plus A. Oops. Yeah. And divided by 2 minus A. And the other one is what? The other entry is 5 minus 2, 6 minus 2A over 2 minus A. Okay. So let's just look at the last 2 rows because those are like the ones that import. In fact, like the only thing that matters is like to see whether they're the same, because if they're the same, you can kill one and then you'll have like rank 3. So like the last 2 rows are 0, 0, 4, a plus b minus 1 minus 2 plus a over 2 minus a, and 0, 0, 2, 5 minus 2, 6 minus 2a over 2 minus a. Okay, so if I do, for example, if I do like minus 2 row 4 plus row 3, if I do this operation, sorry that the space is not too big. Basically, what I want to do is create like a 0 here. You'll get like 0, 0, 0, and then followed by this thing, which is a plus b minus 1 minus 2, 2 plus a over 2 minus a. Obviously, I would never give you something like this on the exam, which because the numbers are just horrendous. But it's just like minus 10 plus 4 b 6 minus 2a over 2 minus a. So this is like the last entry of this row. Like, yeah, like even this even this looks a little bit odd. So this is like the fourth entry of the third row. So if that equals 0, if that all of that equals 0, then you have so if this becomes 0, then the rank then the third row would be 0, 0, 0, 0, and then the rank would be 3. Then the rank is 3. I mean, yeah, so like that's like the equation, like, you know, what's that, because the problem was asking for conditions for a and b. So the condition for a and b is to satisfy that thing. Whatever, I mean, you obviously could rewrite it a little bit so that it looks better, but I'm just saying, right, my intention, like on the exam, like it would be something like a plus b equals 2 or a plus b equals 0, whatever, but it's not, it would never be as long as this. But hopefully the process kind of was making sense. Like the idea was to see how could you make one of the rows exactly 0 so that you would have rank 3. So that's like that would be like a possibility. Okay. But well, we're almost out of time, but that's more or less like the problems I wanted to do. So I'll upload this PDF to the Canvas. I send it to you, and also upload the video to the YouTube channel. So next week we'll continue with eigenvalues, eigenvectors, which is not on this midterm, by the way. It's going to be on the final. So, but hopefully with this and the video from the other class from yesterday, you'll have like extra problems to work on. It's like I tried to do some slightly harder on the review sessions than the ones that will be on the final. So I think that should prepare you as well. So yeah, I'll see you next week unless there are any final questions from anyone. You too. Bye.